Well, hello again everybody. It's been quite some time since I last posted a video, and for that there is reasons. For me, electronics and being in the workshop is really a winter sport, and on the rare occasions when the sun shines here in Yorkshire, I tend to go outside and try to make the most of it. But recently there's been a noticeable drop in temperature, and the nights are really starting to draw in now. So you're probably going to see a little bit more of me. Some of you will probably remember that a few months ago I went ahead and I bought myself a little CNC milling machine. Now of course a lot of people choose to build their own milling machine, but to be quite honest, due again mainly to the lack of time, I decided to go ahead and purchase one that had been pre-assembled. Now having that machine pre-assembled certainly did save me an awful lot of time. I did actually grow up around lathes and milling machines. And if you've watched my previous videos, you'll know that I'm fairly proficient at using CAD packages such as Fusion 360. So it did actually come as quite a surprise to find that the learning curve to use that CNC machine was actually considerably more steep than I had expected. And that's another reason why you haven't seen me for several months. The video that you're watching here shows me using the milling machine for the very first time. And you can see that I'm alternatively spraying some penetrating oil onto the workpiece and the cutter, and I'm using compressed air to blow away the chips that can build up around the cutter. Now most of you men will know that there's numerous reasons why you need to employ some kind of lubricant before plunging in with your tool. That includes reducing the friction between the tool and the workpiece, which results in a reduction in heat and will extend the life of the cutting tool. And when machining soft materials like aluminium, there can be a tendency for the material to get stuck to the cutting edges of the tool. That leads to build up increasing friction, and that can also ruin your dimensional accuracy and affect the surface finish. And the stream of compressed air helps to keep the tool and the material cooler, and also, very importantly, carries the chips away from the cutting tool, because they have a habit of building up, and in fact they can actually jam, again lead to a loss of dimensional accuracy, and also increase that amount of material that can be picked up by the cutting tool, which is bad. And in worst cases it can lead to the tool completely jamming up into the work that you're cutting and snapping the tool. Probably the most common way of keeping the tool lubricated and washing away those chips is to use a flood cooling system. But I don't really want to use a flood cooling system just because I don't want all that fluid sloshing around in my workshop and making a mess. Probably the next most common method of applying that lubricant and coolant is actually to use a misting system. Now misting systems are used quite a lot for big industrial CNC machines, so you've got a mixture of both lubricating oil and compressed air which are fed out from the same nozzle. Compared with flood coolant, the mist system uses much less lubricant, and it can also really rapidly just blast away those chips using the compressed air stream. But a problem of using this type of misting system at home is that obviously this mist gets into the air, you're going to breathe it in, and it can actually have very serious health hazards attached to it. For large industrial CNC machines this isn't a problem because they can operate the mist system within an enclosure, and they can also use some form of air extraction system to actually keep the workshop clear of all those misting fumes and stop the operator from breathing them in. Unfortunately in my small workshop I really don't have the space to fully enclose my little CNC milling machine, and I also don't think it would be particularly easy to set up some form of extraction system. So really I had to look for an alternative solution. But there is a variation on the misting system which stands for MQL, which is minimum quantity lubrication. So again this uses a stream of compressed air, but it just introduces a very small amount of lubricant into that airstream. The idea being that the air provides the cooling and that tiny amount of lubricant just helps lubricate the tool. But one of the big differences over the misting system is that the air pressure is considerably lower and there's less atomization of that lubricating oil, so hopefully we're not going to be breathing that oil in and avoiding the health hazards. Now of course I can't be sure that this is going to work out perfectly. I think the only way to know is actually to try it and find out, so that's what I'm going to do. On the bench here is one of the main parts of our minimum quantity lubrication system. And what it consists of is this semi-flexible pipe here, so we can adjust this at any angle and it'll stay where it's put. And there's a nozzle on the end, so this is where our coolant's going to come out of, and that's going to be a mixture of very fine droplets of our lubricating oil, but also the compressed air, which is going to blow all those chips of swarf away. Now at the other end of this flexible tube we've got a manifold block, and we've got a connector here where we connect a source of compressed air. So I'll go ahead and connect this to my compressor, and we can actually switch the air supply on and off, and that's going to give us some very rough control over the amount of compressed air which is actually going to come out of the nozzle here. Now at the back of the unit you can see we've got this flexible pipe. So this flexible pipe here, one end of the pipe here goes into the lubricating oil, and it actually gets sucked up, it actually gets drawn up along the length of the pipe, and it gets ejected out the end here, and that's caused by a Venturi effect, which is the pressure of the air which is rushing out of this nozzle. It actually forms a partial vacuum which causes our lubricating oil to be pulled from the tank and ejected out of the end of the nozzle here. You can buy these units very cheaply on Amazon or eBay. I think I actually paid round about £8 for this one, so not very much at all. Really, it's amazing that they can actually make and deliver this for the price. Now, although I'm going to be using this as a minimum quantity lubrication system, these are actually designed to be more of a mist system. They actually eject quite a lot of coolant fluid, and I don't want that. And apparently one of the real Achilles heel of these very cheap low-cost mist systems, it's really to do with the mixing of the air and the oil supply. It's done very crudely, and unfortunately it's very difficult to get that adjustment correct. It can be affected by things like the air pressure, or maybe the viscosity of the fluid, and maybe just things like the way you've actually got this positioned on the machine and pointing at the work. So they can be very difficult to adjust, but don't take my word for it. Listen to what these people have to say.
That is not hot at all. I mean, it's just barely warm. It is a little tricky to get the amount of liquid adjusted. It's a bit sensitive here.
The other question that was raised was, these cheap eBay specials with the mixer valves, where you can apparently adjust them on here, adjust the flow, are a bit fiddly to use and don't really maintain their settings, particularly if the tank then runs out of pressure and tops up, they may not be stable.
But because it relied on the Venturi effect to suck the coolant along the tube and out of the nozzle, it was very difficult to get a consistent flow with these type of non-pressurized coolant systems.
And so it would appear that the problem that we have with some of these purely mechanical lubrication systems is that there's all kinds of vagaries that can affect their performance, from the actual mixer valves that they employ, probably the atmospheric pressure, the thickness of the lubricant we're using, and perhaps 1,000 other things which can actually affect the performance. And because they actually use a Venturi, well, other devices you might be aware of that use a Venturi are things like carburetors. Now, when a carburetor is set up properly, they actually work amazingly well, don't they? But if any of you have suffered from carburetor problems, as I have, when they actually go wrong, they can be the very devil. And that's really one of the reasons why we invented the modern fuel injection system, to do away with all those vagaries and the requirement to build such high tolerance parts. I'm going to effectively try to produce my own, I suppose you could call it a fuel injection system, with the fuel being, in our case, the lubricating oil. So I've got one of these peristaltic pumps here. You've probably seen these used on all kinds of equipment. I think these are often used for like dosing fish tanks with various chemicals, whatever it is you put in them. I think I've also seen much bigger ones employed on blood dialysis machines. But the main reason for using a peristaltic pump in this application is that they have a known delivery quantity, which is proportional to the rotation speed of the pump itself. And that means that we should be able to adjust the mixture of the lubricating oil to the stream of compressed air very, very accurately. And of course now we could just use a DC motor to control the speed of this, but I think that probably wouldn't achieve as good a proportional control as I want. So I actually chose a peristaltic pump which has got a stepper motor on it. So I intend to actually drive this stepper motor at different frequency rates so I can get the exact dose rate of our oil correct. Now I'm sure that this is somewhat overkill for this application, but when all you've got's a hammer, well, there you go. Now the other thing that I actually want to do is I want to make the whole thing controlled by the CNC machine itself, so I don't want to have to turn the fluid on or off or turn the compressed air supply on or off. So you can see that I've also purchased, again just from Amazon, again amazingly cheap, I think this was less than £10. This is an air control solenoid, so these are going to be hooked up to my CNC controller so that when the machine starts up the coolant and the mist supply is turned on, and then when the machine turns off it will automatically turn off the coolant and the mist supply as well. So that's what I intend to do today. Now because I chose to complicate our design by using a stepper motor here, we can't just connect a DC supply to our motor here and assume that it's going to start rotating at the right RPM. In fact, if we connected a DC supply to it, it's not going to do anything apart from get very hot. And of course the reason for that is because inside our stepper motor here we've got 4 different coils here, and those coils within the motor, they've got to be energised in the right sequence. Now not only have they got to be energised in the right sequence, we've actually got to swap the polarity of the voltage supply to those windings. So at some point they will be connected positive negative, and at other points those windings will be connected negative to positive. They're going to swap round constantly. So to help me to do that we're going to need some form of driver, and the normal way to drive one of these stepper motors is to use what they call a H-bridge driver, which is going to swap over the voltage supply to those windings. Now it is really simple just to roll your own H-bridge drivers, but for simplicity and ease I decided just to buy an off-the-shelf solution. So this little board here is an A4988 bipolar stepper motor driver, and these modules are used by the thousand in things like 3D printers and those small benchtop milling machines. And they really do take all the work out of driving a stepper motor, because all you actually have to give them is you have to tell them which direction you want the stepper motors to go in. So one of the pins here is used to control the direction, and then you've got another pin here which is called the step pin, and as long as you keep supplying pulses to that pin the stepper motor will spin, and the rate that you supply the pulses to the module determines the rate that your stepper motor will rotate at. Now these little boards do more than that. They do clever things like current limiting and stuff like that, but I'm not going to go into the details of how that works today, so if you're interested just Google A4988 stepper drivers. Now although this little module is super simple to use, again it won't work on its own. We need to give it a direction, we need to supply a string of pulses, and to do that I'm going to use an Arduino. And the reason that I chose to use an Arduino is simply because before today I'd never actually used one before. I happened to have bought boxes of these things many years ago with the hope to use them. Never had, so I thought, well, might as well have a go and use some of those. So we're going to use an Arduino. Again, a bit of an overkill, but what I can do by using the Arduino is I can connect some potentiometers here, so I can actually control the rate or the amount of coolant that we're actually going to add to our air stream. And I've got another potentiometer here because what I intend to do with that is actually have the rate at which this air solenoid valve is switched on. I'm going to have that variable because I'm not quite sure if my small air compressor can run constantly. So again, I intend to kind of pulse width modulate the air supply just to maximise the air that I've got in my shop. Now for a one-off project like this, it would have been quite reasonable to have built the project on some strip board, but I've got to admit I've never had a lot of luck using strip board, so I decided to lay out the circuit and produce my own PCB using KiCad. KiCad really is very easy to use. I think it took me less than a morning to actually download the software, develop the schematics and lay out the PCB board. Now apart from the CNC milling machine, I decided to also treat myself to this Creality 2 20-watt laser engraver. Because for future projects I do plan to spend more time actually building things than just repairing them. So I thought that this laser cutter and engraver would probably come in useful. Now, having spent several months engraving images of my cock on various household objects, I did start to wonder if I could do more with this laser cutter. So I've taken a piece of printed circuit board material and I've applied a mask to the copper side just using some spray paint, and later on in the process I am going to use ferric chloride to etch away the unwanted copper. So I'm using the laser to burn away the paint mass, and that's going to expose the unwanted copper to the ferric chloride solution, and the ferric chloride solution will eat that copper away. I'm sure that most of you will know that there's various types of circuit board material that these things are made out of. Now, one of the most popular one is fiberglass. This is rather old school in that you can see this brown material. This is what I would call Bakelite or phenolic resin. I do think there's actually some advantages to using this old-fashioned phenolic resin. One of them is if you're actually using a router to actually manufacture, to actually mill out the tracks on the board, it's quite an advantage to use the phenolic resin. I mean, phenolic resin isn't nice as a powder, however it's considerably better than having the workshop filled with fiberglass particles that you're going to breathe in. So that's one of the reasons I have this phenolic resin on hand, because I have in the past had to go at trying to mill out a circuit board, which wasn't particularly successful for me. This method does seem to have worked a little bit better. The other advantage to using this stuff is that, one, it's much cheaper than fiberglass because it is pretty cheap and nasty. But the other thing is you can actually see that I've managed to burn in a label, a legend plate here, so we can actually see what all the component values are. If you actually try to engrave fiberglass with the laser, again it just tends to burn it and make a horrible smell, and it can also release those fiberglass particles, so it's not really a good choice to laser. So that's why we're using this old school phenolic resin. Now, one of the disadvantages of using phenolic resin like this is the reality is the circuit board material is pretty rubbish as a material. It would be difficult to build very high specification boards because, you know, the impedance of it isn't very well controlled. The manufacturing tolerances are quite poor in general. Also, just the material is likely to degrade faster than a circuit board made out of fiberglass. I say faster, maybe a fiberglass board will last 100 years, maybe this one will only last 60 or 70, but yeah, it's not going to make any difference for us, and I've got a preference for working with phenolic resin. But one of the main disadvantages of this type of board is that unfortunately the adhesive that they use when they actually glue the layers of copper onto the phenolic resin backboard is the adhesives don't seem to be as strong, and one of the things that you will find is, especially for small or narrow tracks, the actual copper foil has a habit of peeling off, just falling off, and yeah, that's not good from a circuit board point of view. So again, one of the things that I'm going to be trying to do is I'm going to try to keep my soldering temperature as low as possible. When it comes to placing the components on this circuit board here, I don't think there's any particular way that we need to do it. Quite often a process that I employ is that I start off with the smallest components first, and then I put the bigger components in afterwards. And the reason that I do that is because if you put the big components in first, you can sometimes find it difficult to get access to install the small ones. But in this case, I'm not going to do that. Another method that I commonly employ is to actually split the circuit board into kind of functional areas, and I like to concentrate on them. So a nice functional group here would be the 5-volt regulator circuit. So we could put all the components in for that, and then we could test the 5-volt regulator, make sure that's good before we install everything else. But again, I'm not going to do that for a board as simple as this. So all I'm going to do is I'm just going to take all of my components here, and I'm just going to go ahead and just install what comes to hand. So I think I might just start off at the very bottom of the board with all my connectors. So I've got my soldering iron set to 350 degrees, and yeah, I don't seem to have any problem. This seems to be working okay. Well, they seem to go in fine, so I think we'll stick to that temperature, and again, just use a little bit of flux on everything. And I'm going to take my time building this board up. I'm actually working around the tripod at the moment, which makes it more difficult, so I think I'm going to move this to one side so I can get better access to it, and I'm going to carry on. I'll bring you back when we've built it up. Now, previously I went ahead and I pre-selected all my components. Now, some of you are wondering how I choose which component values to use. Basically, it's what I can reach from where I'm sat. That's the main input for choosing capacitor values, in that I've actually got some of the higher values and I need to get up out of my chair to choose them. So I've actually just chosen things which are in easy reach. That's a process that seems to work well with me. I think we'll go ahead and let's stick some capacitors in. I like installing ceramic capacitors. I'm going to do that first, I think. Now, back in the day when I was taught to solder components, they actually said once you'd cut the component leads on, it was best practice just to run the soldering iron over it again, because you could actually get, again, oxidization down the cut edge of the component lead, and that could lead to, I don't know, premature failure of the joint. But yeah, today that just seems like too much effort, so we're not going to do that. So we've got two diodes there which are protecting the regulator, but I remember I've also got another diode in here which is actually, that's a flyback diode, which is, it's actually protecting the switching MOSFET from the back AMF from the air solenoid that we're using. And definitely finding here that although it is a little bit faint, I was able to burn in this legend plate here, and so I can actually see which way round to put the diodes and the capacitors, things that are sensitive to polarity. So yeah, I'm quite pleased with that. That seems to be working well for me. I'm sure some of you have noticed this JBC soldering iron. As you know, I bought this last year and there is a review video on it. I really bought this for surface mount work, but the fact that it is just a little bit smaller than my main soldering iron, which I quite often use on valve equipment and big stuff, it's quite nice to have a little soldering iron. In the past I used to use my big iron bit to do everything. I'm actually a newcomer to these fairly micro irons, but yeah, I'm kind of sold on it. The iron itself, it's okay, nicely packaged. Don't like the fact that the LCD screen here, it seems very close to when you're trying to put it back in the stand. I think it's only a matter of time before I actually stab the soldering iron into the display. I don't know if that would be melting it, but it would be a shame if it did, wouldn't it? In with our 5-volt regulator. I cocked up a little bit here. I probably should have made a hole in the board here for mounting a heatsink, because we're dropping from 24 volts to 5 volts. Although the whole board, it's only going to take a few milliamps, I suspect we'll have quite a bit of dissipation here in this 5-volt regulator. I haven't calculated, but I think it might get a little bit warm to the touch, so I think we're going to end up putting a bit of bent tin on it just to stop it frying. But of course, we'll find out shortly. And seeing as I enjoyed this TO220 package so much, I'm going to go ahead and do it again. in the form of this switching MOSFET, which is controlling the power and turning our air solenoid on and off. Now this MOSFET is actually well over engineered for the job. I think this thing can actually switch about 40 amps. It's actually going to be switching a few hundred milliamps, but again, this is what I had 50 of in the junk box, so again, that's what we're using today. We have a series of 10k resistors which are just used as logic pull-ups or pull-downs or whatever, so we're going to go ahead and stick them in now. And you can see now I was just fumbling a little bit with that resistor. Just goes to show, should have put the smallest components in first, but I didn't want to. Now originally I designed this board to have a few different colour LEDs, so I've got a red one there, a green one. I've also got an amber, but I think a stylistic choice. I don't think I'm going to go for all these multicolour LEDs. I've got quite a few of these green LEDs knocking about, so I think I might just use all green LEDs, which means I'm just going to have to go and rehash just a couple of my resistor values very slightly. So if I use all green LEDs, it means that I can actually use this 330 ohm resistor to drop from 5 volts to the forward voltage for the LED, so I think that's what I'm going to do. My coolant system, it's going to be controlled from an output from the CNC controller, and I always like to, when I'm connecting to something that's external, some other piece of external hardware, I often think it's a good idea to use some optical isolation, some optocouplers, just so we've got galvanic isolation between the two systems. So that's what I'm going to do. So we've got one of these very cheap and unknown branded opto isolators that I bought from Amazon. Let's stick this in, see how it goes. As you can see, we've got the circuit board nearly finished now. Got all the passives involved, the output transistors, the regulator, the pots. The soldering looks pretty good. I was a bit concerned we were actually going to lose some of the tracking. That, yeah, these boards can be a bit fragile, but no problem with that. Soldering seems to have gone very well. The only thing that's going to stop me finishing it is that I've actually got on order some socket headers which need to go on here to mount the Arduino and also the stepper motor control module, but unfortunately they haven't arrived yet, so I'm going to bring you back when we've got them.
The next day.
As you can see, we've finished building our circuit board now. I actually think it's come together quite well. I'm sure that these LEDs are going to look pretty good when they're actually lit up. Now, before we apply power to the board for the first time, I've gone ahead and I've disconnected the Arduino, I've taken that off, and I've also disconnected the stepper motor driver, because just in case I've got something wired up wrong, I think I just want to test for that now so we don't blow up something that could be a little bit expensive. So without further ado, let's go ahead and connect my 24 volt power supply. Now I've actually got a current limit set to about 100 milliamps. I'm not expecting the circuit board to draw very much current with both the Arduino and the stepper motor driver removed. In fact, the only thing that can draw current is this LED, and if I've got my maths right, it should be drawing about 10 milliamps when we apply power. So let's try that now. And we have in fact been rewarded with a glowing green LED. I'm taking that as a slight win, and I'm still of an age where I think LEDs are pretty cool. And our circuit under test is drawing pretty much what I expected. It's around 13 milliamp. The CNC controller that I'm using has some spare outputs, and they can be configured to do a number of different things, and one of those things we can configure it to do is actually to remotely turn on or off the coolant supply, and it'll do that in response to the G-code. So when we write our G-code, we can actually define some commands that we can use to either turn on or turn off that coolant. So we only turn the coolant on when we need it, and we turn it off when we don't need it. Well, I don't have the CNC controller to hand now, so what I've done is I'm just linking some of the wires together just to simulate that. So let's plug this in. Hopefully this LED should then light up. So let's give that a go. Okay, that's lit up. Let's just turn the output from the CNC controller off. Hopefully the LED will go off again. And it does, and make it come back on. Yep, so that's working nicely. And as I mentioned earlier, I'm using an opto-isolator here because it's often not a good idea to actually connect inputs on your Arduino to actually an external circuit, especially there's a possibility that they could be at a slightly different potential. So it's always a good technique that if you're going to be connecting to the outside world, quite often do it through an opto-isolator. Going to install our mode select switch next. So what this allows us to do, we can actually select the trigger source for the board. It can either be remotely from the CNC controller. In the center position of this switch it's off, or we can force the coolant to be on all the time by turning the switch to the far position. So CNC controlled off or manual control. Now to test that, we've got to just wire up a voltmeter, and we've got to look for a 5 volt signal on the input to our Arduino. Before I do that, we've got to find a ground, which I think is on that pin there. And the Arduino input that I'm going to use is connected to pin 12, which should be 4 from the end, so I'm going to count back. 1, 2, 3, 4. Onto there. Now at the moment it should be off, which it is, because our voltmeter's got 0 on it. Now that says 4.5 volts, so I'm not sure if that's in the manual position or the CNC. So I'm just going to disconnect one of these links again. Okay, so that looks like it's in the manual position, because disconnecting the link didn't make any difference. Let's put it in the CNC position. It's on again. This time when we disconnect the link it should go back to 0 volts. Which it does, so our little switch here is doing what it should. So this is a coolant flow control, and I should be able to vary this between 0 and 5 volts. And it's always a good idea when you get the potentiometer wired the right way around, because the number of times I've gotten the wrong way around and it actually goes from 5 to 0 volts. Yeah, I've done that lots of times, but I'm glad to say I did actually get it right this time. So 5 volts, turn it all the way anti-clockwise back to 0. Let's test the air control potentiometer next, so that should be 5 from the end. 1, 2, 3, 4, 5. And it's turned down at the moment, fully anti-clockwise. So let's turn it clockwise and the voltage reading should increase. So that goes from 0 up to 4.9 volts. And I guess that means that our 5 volt regulator must also be working, because we wouldn't have 5 volts in here if it wasn't. And just touching the 5 volt regulator at the moment, it is just warm to the touch. It's not hot, it's just warm. Well, here we are at the very start of the electronics season, and I'm calling shenanigans already. Shenanigans! Because as you can see, my lab power supply has gone into current limit in response to some short circuit on my board. And it's folded back the short circuit current to 110 milliamps. Checking the regulator, that is actually running totally cold. So maybe the problem's not on the 5 volt side. So of course the most obvious problem is on the 24 volt side I'd probably install the capacitor the wrong way around. Quick way to prove that is, let's take the current limit off and see what explodes. I would have thought half an amp will do it. Well, that's disappointing, nothing's exploded. Ow. Okay, so that's the culprit. For some reason it looks like D3 must have gone short circuit, which is strange because this diode really does very little. It's just a protection diode which protects the regulator from being damaged on the off chance that we accidentally connect some kind of capacitive load. Yep, but it's getting hot, so something's definitely gone wrong there.
Al queer! Al queer! Al queer! Oh, going deaf!
Well, how queer. Now of course there's several technical ways in which we could rectify this fault. However, I'm just going to cut the bugger off. One silicon rectified diode later, hopefully you can see we've got our LEDs lit again. So the problem that we had is that the silicon rectifier diode, which is installed across this regulator to give it some reverse protection, that had actually gone dead short. Now I've got no idea why it would have gone short circuit. It certainly hasn't got any stress in the actual circuit in use. The V reverse for one of these 1N4001s is about 50 volts. The maximum voltage reverse this thing's going to see is around 19 volts. So again, it's a little bit of a mystery why it failed. I've taken our failed diode and I've put it under the microscope here alongside some old stock components that I just happen to have. Now one thing that's immediately obvious, you can see that somebody's actually managed to print the band on this diode the wrong way around. So I don't know how that happened, because you can obviously see we've got some new parts here. The band's on one side, but it's actually been printed on the wrong side here, so I don't know what happened there. But there is actually also a noticeable size difference. You can actually see that the body of my old stock components here, it is considerably bigger, but also the legs on the components are thicker as well. So again, I'm not sure, maybe there's been some size reduction over the last 30 years, because these diodes, you know, could have come from anywhere. I'm not sure what the provenance of them is. Using a pair of calipers, let's just measure the lead diameters on these old stock components. So they're, well, about 0.9 millimeters. And let's check our component removed from circuit. So these are 0.6. So the difference between 0.6 and 0.9. So we've got 0.3 of a millimetre, so that's quite a significant difference overall in cross-sectional area. So definitely we could say that the leads of these old diodes would carry more current and have less of a voltage drop. I don't see that that would be in any way significant, because at the end of the day these diodes are actually only 1 amp rating. But I kind of do wonder where I got these 1N4001s. Is this just a modern style of diode? Have we just got some reduction in size? Because it's quite possible that these diodes I've got out my component drawer, they could be 30 years or more old. Don't know where they came from. Probably bought them from a ham radio sale. And I've got some, well, again, some newer diodes here, which also probably came from a ham radio sale, or maybe I even bought them on Amazon. I've got no idea. Are they fakes? Could be. I did actually see that there is some reports of people taking small signal diodes and actually even putting a bigger jacket on them to pass them off as rectifier diodes. Doesn't seem worth the trouble. I actually guess that this probably is a pucker component, and it's just one of those random failures that sometimes occur, but a strange one. Anyway, hopefully no more shenanigans today. As you can see, I've gone ahead, I've installed the Arduino, and I've also installed our bipolar stepper motor driver. Now normally when you install these stepper motor drivers, there is a little potentiometer at the bottom here. You need to set that to produce the right current so that you don't overheat this stepper motor board, and also you could damage your stepper motor, it could overheat. Now there's a way of setting that, but I'm going to do it in a quick and dirty way. Okay, that's running fairly cool, so it doesn't need a heatsink, and that's about right. And as for our 5-volt regulator, well, I can barely touch it at the moment, so I think it's probably running at about 50 or 60 degrees, so I suspect that a little heatsink would actually just reduce that temperature. So we'll go ahead and we will fit a heatsink at some point. I've gone ahead and connected our stepper motor, and as you can see it's actually driving our peristaltic pump, and just so you can see it's pumping, I've put some green dye in this clear tubing, and it's actually just pumping that round quite slowly. So of course the advantage of using this electronic solution rather than the original Venturi is that we've got very fine adjustment here, so we can actually slow that down even more. So that's barely pumping at the moment, or I can actually adjust the potentiometer to actually produce more coolant should we need to. So that's at full speed now, and we can slow it back down. Another advantage of using a more sophisticated control method is we can also do some clever things, like I think it's a good idea that before we start cutting we want to put a good dose of lubricant onto our tool. So what I've done here is onto the Arduino I've just programmed some software here, so I'm just going to turn the controller off, but when it actually starts up it actually just goes into a high speed mode for a couple of seconds, and that's going to introduce some additional coolant in the system. Now that would be quite difficult to engineer that mechanically. We've also got the air solenoid control valve on, and you can see it's turned on, it's actually lit up at the moment. But again, what I can do here is we can actually adjust that airflow. So what I'm going to do is, rather than having the compressed air on all the time, I'm going to have it running intermittently, so let me do that. So now, every few seconds it turns on the airflow, and it also turns on the pump, and then it turns off the airflow and turns off the pump. But we can also just turn off the coolant completely, because for some materials you might not actually want the coolant on. You might want to cut them dry, but just be able to blow away those chips. So at the moment we've actually got the airflow turned on, but we've got no coolant running. But anytime you do want some coolant, just turn the potentiometer. I think in part 2 of this video we're going to build an enclosure for this printed circuit board, and we also need to find out a way of actually connecting the controller to my CNC machine. We've also got to plumb all these various parts together into a usable system, and maybe we'll take a little bit of a closer look at the software within the Arduino. I think the video's quite long enough for today, so until